Okay, so it's almost 3 p.m. So I'll wait for a few more minutes and see if anyone joins, and then I'll get started with this week 3 TA session. Okay, so it's 3. Okay. Okay, so it's 3 p.m. already, so I'll get started with today's content. So since no one has joined yet, I'll get started with solving the assignment 3 problems, which was due last week, and I think you have already got your answer keys. But there were some numericals there in the assignment, so you might face some issues with those. But I think related to the answers and everything, I think this week's content was mostly like all right. But yeah, still let's solve those problems. And if there is time and people join in, I'll move to solve some of the similar questions that you will find in assignment 4. Okay, so the topics that I'm going to cover today will include, so let's write it down. The first I would like to do is assignment 3 solutions. Then second, let's talk about a bit on sensitivity analysis. So probably you won't find many questions from sensitivity analysis in the assignment, but yeah, it's good to know that, and probably the concepts and all should be clear. The numericals could be a bit like long, so that's why I think there were isn't any present in the assignment, but that's fine. Then let's get into this duality and dual simplex method. And finally, let's discuss uh, problems similar to assignment 4. Okay, so let's get started with the first topic, which is the assignment 3 solutions. So let me write down the problems and solve them one by one. Right, so let's see what the first question was. So it says what is the coefficient of artificial variables in the auxiliary objective function z star in phase one of the two-phase method. So as we have already learned in the previous class about two-phase method. So the first problem is what is the coefficient of artificial variables in the auxiliary objective function z star in phase 1 of the two-phase method. Yeah, so the answer will be D, which is -1. So I think that have been discussed in the theory part itself, so that's self-explanatory. Next is if at least one of the artificial variable is positive in phase one of the two-phase method. So in that case, what then the auxiliary objective function it becomes negative, right? So because all the others are appearing with the coefficient 0, and this can have a value of say 0 or 1, so that means it becomes negative. So the second question was if at least one of artificial variable is positive in phase 1 of the two-phase method, then the auxiliary objective function which you try to maximize. So its answer will be C, which is maximization of Z star, that will end up being negative. Okay, so I think that was pretty simple. Yeah, so the third problem was suppose that reduced cost at say minus Cj is greater than equals to 0 for all j at the end of phase 1 while solving the maximization problem using the two-phase method, and let the auxiliary objective function max of z star less than 0 and one or more artificial vectors appear in the final basis with positive value at the end of phase 1. So then the problem will become, the answer will be no feasible solutions. I'm not writing it down the entire problem. So the third one answer will be no feasible solutions because you haven't or you could not eliminate the artificial variables, right? So that means uh, those are appearing and in the basis, and that means that the original variables alone cannot solve that problem, so there is no feasible solution, right? Okay, so that's fine. Let's get into the fourth problem. So let's solve this. So that's using two-phase method. So let's write it down. So this is max of z equals 3x1 plus 2x2. This is subjected to 2x1 plus x2 less than equals 40, x1 plus x2 less than equals 24, and there is another equation, so that's 2x1 plus 3x2 less than 60, and you have your x1 x2 greater than equals 0. So solve this. LP by the two-phase simplex method. Let's get into the solution of this problem. Okay, so for the fourth problem, what you have is that this first, what you have to do, you have to construct or like the auxiliary objective function. So for that, what you can do is that you can also convert it into the standard form first, and then probably you can construct the auxiliary objective function, right? So let's start with this. Suppose, so what you can notice here is that all the uh, constraints are of less than equals to type. So that means you don't even need to solve it by a two-phase method, but because two-phase method is mainly useful when you have the artificial variables. So here you don't need any artificial variables. So, so that means your first step itself will be kind of redundant, the phase one part. But anyway, let's solve it for the sake of completeness. So for the standard form, so let's write down. So what you have is max of z equals 3x1 plus 2x2 plus 0 times x3 plus 0 times x4 plus 0 times x5. So these are the slacks that you will be adding to the less than equals to type constraint. Then you have 2x1 plus x2 plus x3 equals to 40. Then you have x1 plus x2 plus x4 equals 24. And what you have is 2x1 plus 3x2 plus x5 equals 60, and x1, x2 up until x5 all are non-negative. So what you can do, uh, you can construct the auxiliary objective function. So let's do that. Oh, I think I erased it. Let's write it down again. Okay, so that will be max of z star. So as you all know, the slacks and the original variables will appear with a coefficient of 0. And we don't have any artificial variables, so you need not add anything. Okay, so let's do it when by the two-phase method anyway. So in the phase one, what you have is, let me write down, this is CB, then you have B, then you have XB, you have small b, then you have uh, this x1 to x5, x3, x4, x5. This will be the mean ratio column. And let's write down the Cj values. So these are 0, 0, 0, 0, 0. And initially, so this is subjected to same constraints as the original problem. So your initial basis will be x3, x4, and x5, right? So you need not have anything else in the basis. and the CB values are zeros anyway. So this is your A3, A4, A5. This is X3, X4, X5. Your right hand side of those equations are 40, 24, and 60. And your this values are 2, 1, 1, 0, 0. Next one is 1, 1, 0, 1, 0. And the final one is 2, 3, 0, 0, 1. Now let's calculate the reduced cost or the ZC minus CJ. So this is what you have here. Everything will be zeros, right? Because we're multiplying and subtracting also zeros. So that's about it. So if since everything is zero, there won't be any entering variable or leaving variable. So you can proceed with this. So this will be one of the optimal solutions. It will have multiple solutions. But yeah, you don't have any artificial variable anyway. So you have eliminated, and you can start with this solution as your whatever you call it, the initial basic feasible solution. So this x3 equals 24, x4 equals 24, sorry, x3 equals 40, x4 equals to 24, and x5 equals to 60. So this can go as your initial, so the basic solution. And this is feasible as well. So let's get into the phase 2. Okay, so the phase 2 part is very similar. So let's write it down. This is CB, this is B, this is XB, then you have small b, X1, X2, X3, X4, X5, and you have this min ratio column. Here you can write CJ, and let's fill everything. So this is the original objective function is 3x1 plus 2x2. So here it should go as 3, 2, 0, 0, 0. These are the same thing, 0, 0, 0. This is the A3, A4, A5, X3, X4, X5. Let's write down these things. This is 40, 24, 60. The same table that you had as before. This is 2, 1, 1, 0, 0, 1, 1, 0, 1, 0. This is 2, 3, 0, 0, 1. Right. So now what you can do again similarly. So let's calculate the reduced cost. And here it will be different. This will be minus 3, this is minus 2, 0, 0, 0. This one will be the most negative one. So this will be your entering variable. And let's calculate the mean ratio. So this is 40 by 2, 20. This is 24 by 1, 24. This is 60 by 2, so that's 30. So this will be your leaving variable, right? So now, and this will be a pivot. So you have to make it as 1 and others as 0. So let's do this once more. And let's do it this way. So I won't write down the entire thing again. Yeah, so let's so this is the CB column, and here what I have now, and B column, first fill that up. So A1 will come into the basis, then A4, A5, and for 1 it's here it's 3, and for this one is 0, 0. XB is like X1, X4, and X5. Uh, yeah, so that's fine. And now I have to adjust the pivot element and also the corresponding column, right? So the first row you can divide it everything by 2, so that will give you 21, 1, 1, 0, 0. So the next one, what you can do, you can subtract the second column from the transformed, like transformed first column. So that will be 24 minus 20, that's 4. This is 0. This is 1 minus 1, 0. 0 minus 1 minus 1. Uh, yeah, hopefully I've done it correctly. Oh, so I have made a mistake. So I was dividing it everything by 2. So this will be half half. And now you subtract, right? So now it's 1 minus half, so that will be half. 0 minus half, that's minus half. 1 minus, so this is 1, and this will be 0, right? Yeah, so I think that's fine. And the final one, you can just subtract 3 to 1, right? So that's, this one will be 20 again. So this is 0, this is 2, this is minus 1, this is 0, and this is 1. Now let's calculate the reduced cost values. So I haven't written the CJs because CJs don't change. So that's 3 and 2. But anyway, that's fine. So this will be 0. So next one will be 3 by 2 minus 2. So that will be minus half if I'm not wrong. Yeah. For the next one, it will be 3 by 2. Then it is 0. And then it is 0. So in this case, this will be your entering variable, which is x2. And let's calculate the mean ratio corresponding to that. So this is 40, this is 4 by half, so that's 8, and this will be 20 by 2, so that's 10. So this will be a leaving variable, which is like if x4. So now let's solve this. So this will be as before, just one change here. So this is 3, this is 2, and this is 0. Now your pivot element is this one, and you have to multiply it by 2, right? This entire row. So this will be 8, 0, 1, minus 1, 1, 0. So that's, oh, I think this will be 2, right? Yeah, so now this is fine. Next, what you can do, you can subtract the second row from the first row to get the transformed first row. So that will be 16, 1, this will be 0, this will be 1, this will be minus 1, this will be 0. So that is also correct, I guess. Yeah, so that's fine. And for the last one, what you can do, you can subtract. So multiply the second row by 4 and subtract it. So that will be 4, 0, 0. So this will be 1. This is minus 4 and this is 1, right? So this is also fine. And let's calculate the reduced cost values. For the first one, it is 0. For the second one, it is 0. And for the third one, it's 3 minus 2, so that will be plus 1. Next one, it's 4 minus 3, so that's plus 1. And for the last one, it is 0. So everything, so this is for all j. So that means you have reached the optimal solution. So that's x1 equals 16, x2 equals 8. And that means your z max is 3 into 16 plus 2 into 8. So that's 64. So let's see what was asked in the problem. Yeah, so this was asked and the correct answer will be B. So that's answer is B. So that's all about the fourth problem. And let's solve the next one. So next one will have something interesting because it involves the greater than equals to constraints as well. So we have to solve it by two-phase method. So let's do this. Problem 5 is maximize z equals 2x1 minus x2 plus 2x3 subjected to x1 plus x2 minus 3x3 less than equals 8, 4x1 minus x2 plus x3 greater than equals 2, and then you have 2x1 plus 3x2 minus x3 greater than equals 4. And you have this non-negativity constraints as before. So solve the LP using two-phase simplex method. Great. Okay. So now let's do it. So let's start to do it. Okay. So here, what you can do, you can first convert it into the standard form. So for that, you will introduce an x4 here, probably an x5 here, and x6 here. And then you will have two more artificial variables. Let's call them x7 and x8 and solve this problem, okay? So it will be a bit complicated, but let's try and solve this. So the standard form, it's nothing but max of z equals 2x1 minus x2 plus 2x3. I'll add the rest of the things later, but first transform the constraints subjected to. So you have to add one slack here, so it equals 8. Then you have 4x1 minus x2 plus x3. Then what you can do, you have to subtract something from here, so that's x5. And you have to, for that, you have to add something here, so that's equals 2. And next one, so again, you have to do something similar. So that minus x6 plus x8, and that's equals 4. And x1 to x8 all are greater than equals 0. But now what you have is this is 0 x4, 0 x5, 0 x6, and the standard form, you can put any negative m as well, but you can put it as 1 here as well. But generally it's m, so that you systematically eliminate that. But we're not dealing with it anyway. So we are solving it using the two-phase method. So what you can do, you have to construct the auxiliary objective function. The constraints will remain the same for the first phase. So this is nothing but your max of, say, z star equals 0x1 plus 0x2 up until 0x6, and then you have two artificial variables. For that, the coefficients will be minus 1. So let's begin the two-phase method, and let's start with the first phase, right? So let me do that. So this is your phase 1. So let's write down everything. 1, A2, A3, A4. Okay, so I'll run out of space, and these are not A's, I guess these are X's. So let's write down more compactly x1, x2, x3, x4, x5, x6, x7, x8. So there's a lot of computation to be done here in ratio column. And these are your Cj. So this is 0, 0, 0, 0, 0, 0, minus 1, minus 1. So at first, what you will have in the basis is x4, x7, and x8, right? Because those are the ones you can set some positive values to. And that will be your basic solution. So that's a4, a7, a8. And these are will be your coefficients related to that. So that's 0, minus 1, and minus 1. This is x4, x7, x8. The right hand sides are 8, 2, and 4. And now you have to write down the entire thing, right? So basically, it's yeah, it's basically a bit of a painful job here to write, but that's fine. Next one is 2, 3, minus 1, 0, 0, minus 1, 0, plus 1. The final one is, oh, I think I've written it wrongly. So this should be in the next one, right? Okay. And for the middle one, it will be 4 minus 1 plus 1. This will be 0. X5 will be minus 1. This will be 0. This will be plus 1. This will be 0. Okay, so let's solve this. And first step is your reduced cost. So for the first one, it's minus 6, I guess. Yeah, that's fine. For the next one is 1 minus 3, so that's minus 2. For the next one, it's 1 minus 1, so that's 0. For the next one, it is 0. For the next one, it is 1. For the next one, it is again 1. After that, it's minus 1, so plus 1, so that's 0. For the last one, it is also 0, right? So, yeah, let's see which one will be which one will be entering the basis, and this is this one, x1. And let's compute the mill ratio. So this is 8, this is half, this is 2. So what you will have, this one, say a7 will leave the basis, and this one will be a pivot, right? So you have to adjust it, and you have to divide that entire row by 4. So in the next step, what you will have is a4, a1, and a8. And these are your coefficients. This is 0, 0, and minus 1. And this will be x4, x1, x8. And let's adjust the first two. So the first one will be half. And this will be 1 minus 1/4 plus 1/4. This is 0 minus 1/4, 0, 1/4, 0. Yeah, for the others, what you have to do You have to adjust it somehow, and for that, what you will do, you can add first one to the second one. So this will be, I think, 10. Is it 10? No, sorry. You have to add. So it's just calculation. So you divided everything by 1/4 and then you can subtract. So that's 8 minus half. So that's 15 by 2. 1 minus 1. So that's 0. This will be, I think, 5 by 4. Next one will be minus 13 by 4. Then after that it will be 1. Next one will be 1/4. Or think it will be, yeah, it should be 1/4. So that's 0 minus 1 minus 1/4. So that's 1/4. Next one is 0. After that it's minus 1/4. But here, one thing you can notice, you need not go up until the A7, I think, column, because that you can remove. So basically you can remove this one and you can directly go to the next one. So this will be 0. And for the final one, what you can do, you can divide the first row by half and you can subtract, or you can multiply the first row by 2 and subtract. So that will be minus 12, or let's do it in the other way. So you can divide the second row by 4 and you can, or you can divide the second row by, sorry, half and divide, subtract. So that's fine. So let's do this. So this is 3, 0. Then you have 7 by 2. Then next one is minus 3 by 2. Next one is 0. Then it's half. And then it's, I think, minus 1. And then it is 1, right? So let's do this one more time. So yeah, I know it's a bit of a boring work, but yeah, it's fine. Let's minus, so this one will be 0. This one will be 7 by minus 7 by 2. Next one will be 3 by 2. Next one will be 0. Your fifth one will be minus half. Sixth one will be 1. And this one will be minus 1 or minus plus 1. So that's 0. So this one will enter now. So that's x2 column, sorry, variable will enter. And you have to again find out the pivot or the leaving variable. So for the first one, the ratio is I think 6, or it will be 15 by 2 divided by 5 by 4. Next one is negative, so you won't be taking it anyway. The next one is 3 times 2 by 7. So this will be the minimum one, 6 by 7. So A8, so this will be leaving, and this will be your pivot. So that's good news that you are eliminating both the artificial variables in that case. So let's do it one more time. Here what you will have, it's A4, then you will have A1, and then you will have A2, and these are all zeros right now. This is x4, x1, x2, and next what you will have, let's see, you have to multiply that by 2 by 7, so that will be 6 by 7, 0, 1, minus 3 by 7, 0, 1 by 7, minus 2 by 7, and need not write the rest of the things. Yeah, so that's good. Next one is you can do some computations on it. Let's do, how do I do it? So one thing I can do is just check. So that's so multiply by 4 the second one and add it up with the transformed one. So that's 2 plus 6 by 7. That's one way of doing it. So, or what you can do, so to make it a 0, okay, so t by 7. Okay, so let me do this calculation by hand only right now. Let's see if I can get a calculator. Okay. Okay, so let's do it. So let's multiply by 4 and add it up. So this will be 20 by 7. This will be 2, sorry, 4. This will be 0. So this will be 1 minus, this is 4 by 7. This will be 0. So this is minus 1 minus 6 by 7. And this is nothing but minus 2 by 7. Okay, so that's fine. And I think the first one, what you can do, you can mm, multiply by 4 and you can subtract probably. Okay, so multiply by 4 by 5 and then subtract, right? So that will be 15 by 2 times 4 by 5 minus 6 by 7. So that will be 50 by 7. So anyway, uh, you can fill the rest of the part from here, I think. So let's see. So probably in that case, what you will have, you see that all the reduced cost will be greater than equals to 0. But let's see if this is a solution to this original equations or not. So what is my x1 and x2? It's 20 by 7, 6 by 7 and 50 by 7, right? 20 by 7, 6 by 7 and which one? X4 is 50 by 7. So yeah, I think I made a mistake in calculation because it should not have happened like that. Then it will be okay. So let's see where the mistake is. Yeah, up until this point, I think everything was fine. Okay, so now what you can do is to basically, okay, so yeah, now what you have to do, you have to make this one as 0. Okay, so what you have is minus 1 by 4 plus 7 by 2x equals 0. So let's find out the multiplier value. 7 by 2x equals 1 by 4, x equals 1, 4, times 2 by 7. What you have to do, you have to multiply this third one by 1 by 14 and then add it up. So that means it's 3 by 14 plus half. That's 7 by 14, 10 by 14. So yeah, so this will be 5 by 7. Now the next one will be 1. Yeah, this one will be 0. And I think the next one will be 1 by 7. 0 minus 3 by 14 and minus 1 by 14, right? So you can verify the calculations later, but I think that will be that. Next one will be 5 by 4 plus 7 by 2 times the multiplier equals 0. So m is nothing but minus 5 by 4 into 2 by 7. That's minus 5 by 14. So you have to multiply this by. So that means the first one you will get this is 14. So multiply this by 7 minus, so that's 90 by 14. So that's 45 by 7. Yeah. So this one will be 45 by 7. Yeah, I think it's better to do it on Excel, but since doing it by writing, so let's keep it this way. And the next one, I think will be 0, 0 minus 19 by 7, 1 minus 3 by 7, 5 by 14. Now if you can calculate your, so you will get something like I think 0, 0, all zeros, right? So here you will get x1 is 5 by 7, x2 is 6 by 7. So x4 is 45 by 7. So that acts as your initial basic feasible solution now. 5 by 7, 6 by 7. And x4 is 45 by 7, right? Yeah, so let's check this equations. So that's 5 by 5 plus 6, 20. 11 plus, yeah, so the first equation is correct. Second one is 20 by 7 minus 6 by 7. So that's 2. That's also correct. Third equation is 2. So that's 10 by 7 plus 18 by 7. So that's, yeah, 4. So that's correct. Yeah, so this is the correct starting point. And now perform the normal simplex table. So proceed with the, say the phase 2, which is the simplex method. So it's now starting with this solution. You can just uh, complete the entire thing, right? So I'm not going into the detail, but so that's all about the fifth problem, and where you will notice that uh, I think once you solve it, you will have Yeah, you might notice something interesting. So uh, so here, I think while trying with this min ratio test, if every ratio turns out to be negative, then that means you have unbounded solution. So that will be the case here. Even if you have some entering variable, you don't know the leaving variable. So here, the problem I think asked you about the answer. So answer will be B here. So this will be unbounded solution. Yeah, you can check with the rest of the portion by solving the simplex table, right? Okay, so let's write down the sixth one. So it says that degeneracy occurs when, yeah, the correct answer will be C, when some of the basic variables are zero, right? Have zero values. Okay, so I think that's fine. Let's move on to the seventh problem. So when there is a tie in selecting the departing vector, the next solution is bound to be degenerate. So that's the answer. So let's write down. So that will be A is the correct answer is. Yeah, so let's get into the eighth problem. So it asks you to solve another LP, and uh, and you have to check whether you have an optimal solution or whether you have a degeneracy anywhere or not. Okay, so the problem is, so let me write down. The next one is, I think we talked about a similar thing in the previous class as well. Okay, so that's the problem. Now, if you can notice, what you can do, x1 and x3 doesn't appear in both the equations. Uh, so what you can do, x1 equals 0 and x3. So x1 equals 0 and x3 equals to 1. So that's the initial VFS. But x1 is a basic variable and it is 0. So that's stage 1 or type 1 degeneracy. So automatically, option C is eliminated. And we have to check whether you have an optimal solution or you have some subsequent degeneracies or not. So it might have multiple answers to it. So option A is correct for sure. And if you solve this problem, you can notice that you have two equations, and anyway, need not solve the entire problem. Anyway, you try to maximize something, and x1 and x2 are non-negative, and the first equation itself says two of the things are adding up to 0, right? So the x1 equals 0, x2 equals to 0, so this will happen for sure, and x3 is 1. So that's the your solution, and z max is nothing but 1. So answer will be A and D. So that's pretty simple. Okay, so let's have 9 and 10. So two more problems were there in assignment 3. So the ninth problem is you have to again solve. So minimize that. So as you can notice that the previous problem had artificial variables, and with so many variables it's pain to solve it by hand. So you can just compute everything in Excel, so that would be helpful. By formulas you can use it. But yeah, so this problem, it's all again less than equals type, and so that means that's good news, because you have to, you can just deal with 5 variables. Okay, so solve this LP by simplex method. Okay, so I'm not writing the standard form on those things as such, or I can write it down as well. So let's proceed with that. So you have to convert it into a maximization problem. So max of minus z, so that will be equals 7x1 plus 12x2 plus 16x3 plus 0x4 plus 0x5, because those will be your slacks that you add. Oh, missed one here. And for the next equation, it's 5, and x1, x2 up until x5, it is greater than equals. So now let's solve it. CB, B, yeah. CB, B, XB, small b, and ratio test, and here it's CJ. Now this is 7, 12, 16, 0, 0. Initially x4 and x5 are in the basis. These are your 0, 0. So it's good that you have only 2 rows to solve here, right? So that's easy by hand when you are doing it. So let's the right hand side is 1 and 2. 2, 1, 1, 1, 0. This one is 1, 2, 4, 0, 1. Now let's compute your reduced costs. These are your minus 7, minus 12, minus 16, 0, 0. This will enter. This will be 1. This will be half. This will be your pivot. Let's move on to the next stage. So this will be leaving. Okay, I'm not writing this. So here your bases will be A4 and A3. This is 16, this is 0, this is x4, x3. Now you can divide this by 4, so that's half, fourth, half, 1, 0, 4. Okay, next one you can just subtract whatever you have got from this one. So that's half 7 by 4, half 0, 1 minus 1/4. So let's do it again. So as you know, it's all the same technique and you can even solve it in Excel, so that's not a problem. Minus 3, so that's 8 minus 12, so that's minus 4. Then you have 16 minus 16, so that's 0, this is 0, this is 4. So this one will enter now, and again you have to do the same check. So this is 1, this is 1, because half divided by half. Now you have a tie. So you have a tie, and that means you have degeneracy in subsequent steps. But that was not an option. You want the current, the actual solution. So what you have to do, you can treat A1 equals old A3, A2 equals old A4, and A3 equals old A5. So the min will be min of A11 by half, comma Y21 by half. So that's min of 0 by half, 1 by half. So that's 0. So that means what you have here is that A2 or the old A4, whatever you call it, so that will be your departing run. So these are the halves that's coming from here, and Y11 in this case was 0, and Y21 was this one. Okay, so what you will have here is that uh, the new vector A2 will be the entering one. Sorry, the leaving one. A2 or the old A4. That is old A4 as the departing variable. So that's the critical part of this problem. Now you can solve it one more time. So what will happen? This will go out. So you need to avoid the cycling that we talked about in the previous class. So that's why you have done it in this way. So now let's CB, XB, B, small b, let's write it as x1, x2, x3, x4, x5, CJs. These are your 7, 12, 16, 0, 0. If I'm not wrong, I've written it correctly. Next is that this becomes your pivot. So multiply it by 2, so that entire thing. But first let's write down A2, A3, 12, 16, x2, x3. Okay, so this one is 1, 7 by 2, 1, 0, 2 minus half. And next is just subtraction, so that's 0, minus 3 by 2, minus 6 by 4, 0, 1, minus 1, half. Let's calculate this. So this first one will be 42 minus 24, so that's 18 minus 7, that's 11. Next one is 0, next one is 0, that's 24 minus 68. And this one is 8 minus 6, so that's 2, right? So now that's good news that have for all j. So the optimal solution is x2 is 1, x3 is 0, so that means your x1 is also 0. And you were solving a minimization problem, the original one, minus 7x1 minus 12 minus 16. So that's minus 12. So let's see if any of the options were matching. Yeah, so option B is the correct answer. So yeah, let's move on to solving the 10th problem. So again, you have to solve an LPP by simplex method. So everything has the same flavor except for like degeneracies and those things, minor details. X1 and X2 are unrestricted in sign. So that's the only change that you have. So let's convert into the standard form. Solve this LP by simplex method. Okay. We have some water and so right. So yeah, let's solve this. So you have to find the variable values and the objective function. Now let's do this. So standard form. First we have to write down this. So for that, what you have here is that you can write x1 equals x1 prime minus x1 double prime, and x2 as x2 prime minus x2 double prime, right? And when you do that, you assume that x1 prime, x1 double prime, x2 prime, x2 double primes all are greater than equals 0. Now it becomes max of z equals 2x1 prime minus 2x2 x1 double prime 3x2 prime minus 3x2 double prime, and you will have 0x3 plus 0x4 corresponding to those two equations. Sorry, 3 you have, so that's 0x5. Next one is subjected to minus x1 prime plus x1 double prime plus 2x2 prime minus 2x2 double prime plus x3 equals 4. Then you have x1 prime minus x1 double prime plus x2 prime minus x2 double prime plus x4 equals 6. Then you have x1 prime minus x1 double prime plus 3x2 prime minus 3x2 double prime plus x5 equals 9. And you have this non-negativity constraints as well. So it's now, again, you have to do some sort of calculations based on it. And I think it will take you like 4 simplex tableau to solve this. But the rest of the part is just proceed with simplex tableaus. So it's the same steps. I'm not going into the details of it. Finally, I think 3 of the variables will be in the tableau. So that would be, I think, x1 prime is 9 by 2, x2 prime is 3 by 2, and I think x3 will be 11 by 2. So in that case, what you will see is that x1 will become 9 by 2, x2 will become 3 by 2, x3 will be 11 by 2, so that's fine. And your z max will be 2x1 plus 3x2. So it's 2x1 plus 3x2. 9 plus 9 by 2, so that's 27 by 2. And in that case, your option C will be the correct one. So anyway, here, even if they were unrestricted in sign, they turned out to be positive. So it's fine. But it could have happened that those variables turned out to be negative. So that's all about this assignment 3 solutions. Yeah, I think you already got the solutions maybe in the course page. I'm not sure, but at least the answers, I think just the answer key was posted. Yeah, but this is the detailed solution that we can do in this way. And I know it's very hard to do it by hand, and I think it's better that you do it in Excel or something, so that would be easy. But you need to understand the method, that's all. Okay, so yeah, so this is the assignment 3 discussion that I wanted to do. And for this week's content, the assignment 4 is due on this Wednesday. But yeah, so I wanted to discuss the similar things in like similar problems that you will find in assignment 4. But since no one has joined, I'm not sure whether it's good to discuss it today, because anyway, I expect that you don't have like I'll assume that you don't have any doubts, so probably will be able to do it on your own since you are. joined, but yeah, let's see what I can cover or the remaining time, because this last 1 hour was supposed to be question answer type, but since no one is here and I already solved some 10 problems, so I'll just probably wait till 5, and if anyone joins and asks questions, that will be fine. Otherwise, I'll close the session at 5. But yeah, so the main things that rest of the things that I wanted to discuss is sensitivity, and then a little bit of, so if I go back, so it will be sensitivity, duality in dual simplex, and problems similar to assignment 4. But yeah, so let's probably briefly discuss it since we have around 45 minutes left. And probably I'll just briefly talk about what are the kind of techniques out there or the main problems that are out there. So, what you have, let's write sensitivity analysis. So, in sensitivity analysis, first of all, you can have variations in cost vector C. So, you won't find much problems related to this in the assignment, but it's good to know these things. So, suppose what happens is that this max of say z equals cx or c transpose x, whatever you like to write, subject to say x equals b, x greater than equals 0, so it's in the standard form. Now suppose c, uh, for kth component, ck star is nothing but ck plus delta ck. So in that case, you know, so first check for feasibility. So xb is nothing but b inverse b. So this is independent of c. So that means your initial basic feasible solution will not change. The initial BFS will not change. And for optimality check, what you have is set k minus ck, so that's kind of cb times yk or something that you have. So here the ck is appearing, so optimality criteria may change. Okay, so in the simplex tableau, if you notice, you have the set j minus cj. So for a particular case, so it will be set k minus ck. So in that case, these are your basic uh, variable coefficients. So if these cost vectors are not changing, then that means your original solution will also be unchanged in that case, because it's just the corresponding multiplications and so on, and for the rest of the things it will be 0 anyway. So just to observe this, yeah, so I'm not wrong. So suppose I change x1 here, and in that case, so if I increase it by a lot amount, 18 or something, okay, so let's get into the initial tableau. So let's see, try to understand. Mm, so these are okay. But I think there is an issue even if you change this CK. Okay, so house to CB. Okay, so yeah, so the idea is suppose you have your CK not belonging to CB. So it says that optimal solution will be unchanged. And if CK belongs to CB, in that case, what happens? You have to calculate the range in which the optimal solution will remain changed. So if your delta CK is in this range, your variable values and everything will not change. Or this will be less than. And Z star will improve by delta CK times XK. So that's the idea of this first one. And next is changes in the requirement vector B. Okay, so let's try to do this. What you have is say x equals b and x greater than equals 0. Now bk star, suppose I write it, it becomes bk plus delta bk. And initially, the new BFS will be B inverse B star because this has changed. And your B star is nothing but B1, B2, BK plus delta BK. So this is the change has occurred. This is Bn. So you can write it as B inverse B plus B inverse 0, 0, delta BK Bm. And finally, if you just pick the kth column vector of B inverse, you will get this, right? So beta k is nothing but kth column vector of B inverse. All right, so this is fine. And you can also write it like this: xbi star plus xbi plus beta ik delta bk. So beta ik is I comma kth element. So this is for corresponding variable, right? of B inverse. So the feasibility check is nothing but xbi star greater than equals 0 for all I equals 1 to m. So that means xbi plus beta ik delta bk greater than equals 0 for all I. You will again get something like beta ik if beta ik is greater than 0 or delta bk less than equals minus of xbi plus beta ik if beta ik is less than 0. So that means what you can put here is that if max of minus xbi divided by beta ik greater than 0 less than equals delta bk less than equals min of minus xbi divided by beta ik less than 0, then all solution will remain feasible. And what you have is the optimality condition. So that's J minus Cj, it's nothing but Cb Yj minus Cj greater than C. So this is independent of, so this will remain as optimal. So that means if your delta bk is in that range, your optimal solution remains optimal, otherwise you have to resolve the problem. Okay, so that was about the second one. And the third one was change in the elements of the coefficient matrix. So I'm not going into the details of it because it was also discussed in the class, and it's like a bit of a complicated mathematics involved. So generally, I think there are two cases that arises here. It's whether AK belongs to doesn't belong to the basis, or the second case will be AK belonging to the basis. And you have to do both this feasibility and optimality checks, and you will again get some ranges in which your optimal solution remains optimal. Okay, so why do we do this? Because we need not solve the LP again if our changes in the certain ranges. So just up to avoid some extra computations. That's why this is necessary. And yeah, so next will be addition of a variable. So there, uh, suppose you have max of z equals cx plus cn plus 1 times xn plus 1, subjected to a, then cn plus 1 xn plus 1 equals b, x greater than equals 0, xn plus 1 also is greater than equals to 0. So for optimality, what happens? Zn plus 1 minus n plus 1 if it is greater than 0, and for all j, then this optimal solution will remain optimal. and your new variable value will be 0, right? So that's as simple. Otherwise, if there is some change, then you have to do some recomputations of the problem. Okay, and the last one is addition of extra constraint. So, as we already know, this geometric view, so suppose this is one constraint, this is one. So probably this is your original region. In simplex method, we start with a feasible point and that to a corner point, right? And you move from one corner point to another. So suppose you add another extra constraint. So if that is somewhere here, then it's not like playing any role, right? Your feasible region will still remain feasible and you can solve the problem. But suppose it is chopping off certain parts of it. So probably this is your transformed solution space. And these two corner points no longer belong to the feasible region, right? So these are your new corner points that you have created. So in that case, what will happen? If you start from this corner point, that solution will not be feasible, right? But you can start with that. So that's why you go for dual simplex method. So this dual simplex method is used for this reason. So where you need not start with a feasible solution. So infeasibility is fine at the beginning, but you start with a basic optimal solution. That optimality is in the sense of that can violate feasibility. And then finally, what you have to do, you have to check and get to a feasible like solution, right? So that's the idea of dual simplex method. But let's see if I want to solve something or not related to this. Okay, so yeah, in regard to the sensitivity analysis and all, the shadow prices and all, I haven't discussed it, but yeah, that is also another thing that one can look at. Okay, so I'll get into the duality theory a little bit, but and dual simplex method. And let's see, I have half an hour left. Okay. All right, so let's start with this duality theory. So suppose this is my primal problem. When of say now I can write a C transpose X in the vector form subjected to say AX less than equals B and X greater than equals to 0. Now my dual problem will be, oh, let's keep this as max because constraints are of less than equals to time. The min of B transpose Y subjected to some this A transpose Y less than equals, oh sorry, this would be greater than here. This is greater than equals C transpose and Y greater than 0. So let's give an example. And also the dual of the dual is also um, like what do you call, and you get back the primal itself, right? Okay, so to give you an example, so this is x1 plus 2x2 subjected to x1 plus 4x2 less than equals say 22, and 3x1 plus 2x2 less than equals 16, x2 less than equals 3, x1, x2 greater than equals 0. So let's convert it. Uh, so this is in that form only. So the primal form, this is max of z. So now the corresponding dual will be min of B transpose Y. So here, so corresponding to this, let the dual variable be Y1, this will be Y2, this could be Y3. So in this case, what will happen is that, what you will see is that 22 Y1 plus 16 Y2 plus 3 Y3 subjected to 3 Y1 plus 3 Y2, and that will be greater than equals to 3, and for the next one it will be 4y1 plus 2y2 plus y3, that will be greater than equals to 2, right? And your corresponding variables will be greater than equals 3. So this is how you convert it, but there are rules, certain rules. Suppose you have an equality type constraint, so then what happens, right? So now suppose I give you, suppose your primal form is max of C transpose X subjected to AX equals B, next greater than equals 0. Now what will happen? So in that case, what you can do, you can convert this into AX greater than less than equals to B and AX greater than equals to B. So both are kind of together valid. So this one you can convert it as minus AX less than equals minus B. So now your primal problem looks something like this. So you have one set of constraint ax less than equals b, another set of constraint a minus ax less than equals minus b, and this x is greater than equals 0. Now when you convert it, so it will be min corresponding to this. Suppose y1 is the dual and y2 is the dual variables. What will happen is that you will get b times y1, b transpose times y1 minus b transpose times y2 subjected to, this one would be a transpose uh, times let's see, yeah, let's see here. Okay, so a transpose times y1, this one will be minus a transpose times y2, and that will be your greater than equals to ct. And what you will have in addition to that is y's are greater than equals 0. So it's y1, y2's are greater than equals 0. So what you can now notice is that you can take this as common, and from here also you can take this as common. Now you can treat y1 minus y2 as y. So that means since both are positive, so y will be unrestricted in sign, and the dual form will be min of B transpose Y subjected to A transpose Y greater than equals CT. Y is unrestricted in sign. So whenever you have this equality type of constraint, the corresponding dual variable will be unrestricted in sign, and suppose some of the primal variables are unrestricted in sign, so the corresponding dual constraints will have equality type. Okay, so that's the idea of conversion in this duality theory. Let's get into the dual simplex method a bit, and then I'll probably discuss the assignment 4 problems briefly if I have time. So the dual simplex method. So here, the thing is that first you will decide which variable leaves. So it's kind of opposite to what you have been doing. So the leaving variable, yeah, so the criteria to choose it is nothing but min of I xbi such that xbi is less than 0. So that's just first you do this. Then next you do the entering variable check. So earlier you were doing some min ratio test or something to check for leaving variable, but here uh, two cases might happen. So if yRj is greater than equals to 0 for all j, so that means no feasible solution. And yeah, we'll see more of it when you solve a problem. If yRj is less than 0 for at least one j, then you have to compute zk minus ck divided by yrk equals max of zj minus cj divided by yrj such that yrj is less than c, right? Okay, so this is one thing. There is something called artificial constraint method, but I'm not going into that because that's anyway not used. Okay, so let's move on to the assignment 4 discussions briefly, and then I'll probably wrap up the session. So it's around 20 minutes left. Okay. Okay, similar discussion to assignment 4. And probably since the deadline is around this Wednesday, in next week's class, I can solve specific doubts related to the assignment 4 questions directly. And yeah, I'll go into the solutions in more detail next week. And probably some of the new topics I might discuss. But anyway, I think the course content is very simple to follow till now. So probably that's why people are now joining in. And yeah, I think, and the problem structure is very similar to one from another, and it's, I think, very simple for everyone to formulate and solve it. Yeah, I hope things will get more interesting later. Okay. Yeah, so the first problem is just a theoretical problem, so that's related to the, I think, the sensitivity analysis. When you change the cost coefficient, so you do some sort of a reduction with corresponding to a non-basic variable. So will the optimality effect gets affected or not? So that's fine. I think I have discussed similar things today. Then I think the next problem was is related to the changes in the right hand side of the vector. So that's the requirement vector, and you have to check for in which range the current optimal solution will remain feasible. So I think that is also discussed in this. Then what you have is some following statements about true about dual LP. So yeah, so that's related to something on bounds and all. But yeah, I think if you go through the lectures carefully, then you'll get the direct answer. I'm not going into the that. The fourth one is which of the following statements is or are true. So that means there could be multiple statements that are true. So be careful with that. So I think it's very similar to the what happens if one of the variables in primal cell is unrestricted. What happens to the corresponding dual? So that I have just discussed now, and then primal, suppose that's constraint in its equality, what happens to the corresponding dual or something. So I think that's pretty simple and you can get it. So that's first four problems. Fifth problem is again, you have given primal, you have to write the dual expression of it, and I think I've already discussed how to do that. So convert it into standard form that is shown, and then you can get the dual form as well. Sorry about that. So let's get into the next one. So construct the dual of the LPP, solve both the primal and dual problem. Okay, I'll just have some water. Okay, so sixth problem is that. Seventh is also construct the dual and solve both the primal and dual. Eighth one is also use duality to obtain an optimal solution to some equation. So I think it's better that yeah. So that's again pretty simple. Ninth one is which one is true related in dual simplex methods. So that's related to feasibilities and optimality. So that I think you can answer easily. Tenth one will be which one like true about some departing or entering variable. So I think that's pretty simple as well. So those are discussed. So let's solve one problem which is similar to that you will probably find in assignment. Okay. So the theory part is all you can answer. So let's try and solve this. Say max of z, say 6x1 plus 8x2, subjected to, say I give you x1 plus x2 less than equals say 14, and say 2x1, sorry, um, yeah, so probably I'll give you 2x1 plus 3x2 less than equals say 24, and x1 is less than equals say 9, right? And x2 is less than equals say 7. x1 and x2 is greater than equals 0. So you have four equations, and you can convert it into a dual, and then you can solve both the primal and dual. So that's the idea. So this is your primal. So you can solve it. So solve by simplex method. So I'm not going into the solution method because that you already know, and you can also do it in Excel. For the dual construction, what you will have for this one, you will have y1 as the variable. For this two, will have dual variables y2. For this one, y3. For this one, y4. So these are your dual variables. Now let's write down the dual. So that's min of 14, and all are less than equals to type, and all are unrestricted in sign as well. So that's fine. So that you have two variables here in primal. So you'll have two constraints in the dual version. So yeah, so those are the correspondence that I think you already know. So that's 24y2 plus 9y3 plus 7y4 subjected to, you have y1 y1 plus 2y2 plus y3, that's greater than equals 6, and you have think y1 plus 3y2 plus y4, greater than equals 8. And since all of those are less than equals to type, so you have this as greater than equals 0, right? Now, again, you have another optimization problem, an LP, and you can again solve it by simplex method. So you can solve by simplex method, or you can solve the primal version using dual simplex method. So there are some connections with, so if you want the dual variable values, that has some connections with, I think, the reduced cost values that you get from the dual simplex tableau. So yeah, I think you'll get it. I'm not going into the details of it because anyway you have to solve this assignment. Yeah, so that's more about it. So what you can do, probably you can just put this two versions of the problem in Excel and check which is the optimal solution. So yeah, that's one way of doing it. Then probably another will be, again, uh, it might happen that so I think that was talked about that both primal and dual problem might be feasible. So that's one thing. And it might happen that primal is feasible, but dual becomes, say, unbounded or something, or dual is feasible, but primal becomes unbounded or something. So that might happen, right? Uh, so, so just you need to check what happens in that case. So unboundedness, you already know how to check that. So it's typically when you're in the mean ratio test, everything becomes negative, right? And also, it might happen that dual, when you try to construct a dual, it might happen that it has no feasible solutions as well. So that's another check you can do, right? Okay, so or dual might have a feasible solution. So, but in dual simplex, we don't need feasibility to begin with. Anyway, so that's fine. And again, you can use duality to solve another problem, which is pretty similar. Yeah, dual simplex method is very useful when you have, say, lesser number of variables but very high number of constraints. So when you probably duality theory, you can convert it and make it as very probably high number of variables but less number of constraints. So probably that's easier to work with in certain cases, but yeah, in solvers and so on. So in that case, dual simplex works well. And yeah, dual simplex typically you can, since you need not have a feasibility to begin with, you can just keep on satisfying the optimality criteria and then get the solution, right? Okay, so that's the most, like, the idea behind this problems, and I think you will get and you will solve it. So let's since I have some 7-8 minutes left, let's do one more exercise. Uh, so let's try and convert this primal to dual. So this is max of, say, z equals 5x1 plus 2x2 subjected to, say, x1 minus x2 less than equals 2, say x1 plus x2 greater than equals 5, and say x1 minus 5x2, it's less than 10, x2 is greater. In that case, this will be one dual variable y1, this will be y2, this will be y3, and the dual version now, so you have to be careful, right? You have to convert it into less than equals to 10. So this is nothing but minus x1 minus x2 less than equals minus 5. Yeah, so that's the advantage of this dual simplex method. When you have this right hand side as non-negative as well, sorry, negative as well, you can start from that solution because you allow your variables to violate feasibility. Okay, so anyway, uh, let's write down the dual version. So dual will be a minimization problem, and you have 2y1. Now here you have to be careful, right? Because you have converted that inequality sign. So that will be minus 5 by 2. That's not plus, so you have to just be careful in that. This could be your 10 by 3. Now subjected to very similar things. That's y1, but here you have to pick minus y2 plus y3, and that should be greater than equals 5. And the next one will be minus y1 minus y2 minus 5 y3, that will be greater than equals 2. And since all of those were less than equals to type constraints, so these are non-negative. Yeah, you can also work with this variable and start, like even solve it directly as well, the dual problem. So that's mainly the idea behind it. Yeah, so convert it into the standard form. So that's the main idea. So probably another one would be some say max the min of 3x1 plus 2x2 subjected to 5x1 plus 9x2 greater than equals to 15, x1 plus x2 equals 7, and say x1 greater than. Now how do we do that? So this is not even in the standard form in primal, so you have to convert it, so that will become max of minus 3x1 minus 2x2 subjected to minus 5x1 minus 9x2 less than minus 15. This you can keep it as equality, but later you have to deal with it. Anyway, so let's do this. So suppose this y1 is the corresponding dual variable. For this one, corresponding dual variable is y2. Now let's write the dual. So that will be a minimization problem. And here what you have to do, you have to pick this right hand side. So that's minus 15y1 plus 7y2. And now this is subjected to this minus 5y1 plus y2. Now this will be greater than equals minus 3. And the next one will be minus 9y1 plus y2. So since the corresponding this variables are of greater than equals to type, so this will be also greater than equals, and this will be greater than equals to minus 2. Now corresponding to y1, the constraint was less than equals to type, so y1 is greater than equals 0. But corresponding to y2, the constraint was of equality type, so that means your y2 becomes is unrestricted. So that's the idea behind this conversion, right? Okay, so I think it's almost 5, around 3 minutes left. So that's how you can convert your primal to dual, and also you can again do from dual to primal. So let's do that exercise and see if we get back that as well. So now here let's pick x1, let's pick x2. So that's we are trying to get the dual of dual. And it's kind of in the standard form right now, so that's fine. So what you can do, it's minus, so it will be max of minus 3x1 minus 2x2 subjected to, again it will be this one minus 5x1 minus 9x2 less than equals to minus 15. So that means it's nothing but 5x1 plus 9x2 greater than equals 15, right? So that was the original one. So that's fine. And that means this one is nothing but min of 3x1 plus 2x2. And for the other, uh, this is x2, right? But you know, y2 is unrestricted in sign in the previous one. So that means the corresponding uh, constraint has to be, uh, in that case, it will be of equality type. So that means it's x1 plus x2 greater than equals to 7, not greater than. So it will now become equal to 7 because of that extra addition that you have. And that was there before. And since both those constraints are of greater than equals to type, so you have x1 and x2 greater than equals to. So you get back the original one. So the dual of dual, you get back the primal. Yeah, the solution techniques are same and all, so I'm not going into the details. So that's mostly the discussion of assignment 4. So I think you'll be able to solve it easily. Yeah, I think the content was easy, so that's why no one joined, but that's fine. Next week also we'll discuss similar things because the assignment 4 problems are on dual simplex and itself. So probably again I'll take one or two example problems and solve it, and probably we'll discuss some of the theories that will be covered next week. But yeah, mostly if you have doubts, you can drop by, otherwise it's fine, or you can post it in discussion forums. So that's all. Yeah, so it's 5 already, so I'll stop the session for today and see you in the next week's content. Okay, so thank you. Hope you will listen to it later.